Our last section for this week is on three different topics. Okay, one they're called continuity, intermediate value theorem, and end behavior. Okay, they're all kind of related, so we'll just go through them and see what they mean. Okay, most graphing calculators assume that graphs should be connected. Okay, here's a graph that should not be connected, and it handles it just fine. Okay, it draws it exactly the way it should be drawn. Older calculators would draw it like this. It's the same graph, but what the calculator is trying to do is connect everything together. Okay, because that's the kind of graphs the calculator likes. These vertical lines should not be here. They should not be connected. These are what we call asymptotes. Okay, we have vertical asymptotes in this graph, and we'll learn more about what those are if you're not familiar. But newer calculators can automatically detect when a graph has these things called asymptotes and doesn't put them in if they shouldn't be there. Okay, old calculators, you didn't have a choice. They were always there, and they look kind of confusing. Okay, but most calculators assume that graphs like to be connected unless you've got a feature that can handle things like this situation. Right, so let's try graphing a couple of these. I'm going to graph 1 divided by x minus 3. Okay, and I'm going to just put a picture of it off to the side. And I'm also going to graph the integer function. Okay, if you want to graph these with me, you can, or really all you need to do is look at the pictures, and I'm going to ask you a question about them. Okay, here's your integer function. Okay, and the last one I'm going to graph is x squared minus 2x plus 4. Okay, so x squared minus 2x plus 4. Let me do zoom 6 on this one because I'm not seeing much of the graph. Zoom 6. That's better. Okay, and my question about all of these graphs is, can I trace along these graphs without lifting my pencil? Let's look at the first one. Can you trace the graph of f of x without picking up your pencil? Okay, no. Okay, there's something weird happening at 3. Okay, because we'd be dividing by 0. So this one you can't. How about the integer function? Looks like steps. Nope. If you turn off detect asymptotes, what the calculator will do is it'll actually connect the steps. They should not be connected. Okay, so this one you cannot trace. How about the last one, h of x? Yeah, you could tell me, put my pencil anywhere on the parabola. You could tell me some other point you want to go to, and I could get there without lifting my pencil. So this idea of whether we can trace along the graph, whether either lifting or not lifting our pencil, has to do with what's called continuity, okay, or a continuous interval. Okay, so basically the idea of a continuous interval is that you tell me two numbers, a and b, and then I ask myself, can I get from a to b on your graph without ever lifting my pencil? If I can, then the interval you just described to me from a to b is called continuous. If you give me an interval and I have to lift my pencil to get from one part of that interval to the other, then that's called discontinuous. Okay, so any questions on that idea? Continuous. All right, so it's possible to have some functions that are continuous on certain intervals, but discontinuous on other intervals. For example, if I go back, let me just copy one of these pictures. Let me make it bigger. If you give me this picture, I can definitely name some intervals that it's continuous over. Okay, I can pick various intervals and be able to trace from one point to another without lifting my pencil. But there are certain points that if you gave me, like you said, trace from -1 to +3. I could not do that without lifting my pencil. Okay, I would start tracing along, then all of a sudden I'd have to lift up and go to the other section. Okay, so that's what I mean by saying for some graphs it's possible to be continuous over some intervals and discontinuous over others. Okay, so I'm going to take the graph of 1 divided by x. I'm just going to put it on top of the other one I have. And I want you to tell me 2 intervals over which this function is continuous and 2 intervals where it's discontinuous. Can anybody give me an interval on this function? Give me an x value to start, give me an x value to stop, and I could trace from those 2 values without lifting my pencil. Yeah?
-7, -2.
Sure, -7 to -2. Are you using parentheses or brackets? Or both?
Both.
Okay, which one do you want where?
You can just put a bracket on -7.
Sure.
And then put a parenthesis.
Yeah, it doesn't really matter whether you include 2 or you don't include 2. The point is I can trace over that interval without picking up my pencil. Right? Can somebody give me another interval? Another interval over which that's continuous? Yeah, Sophie? Negative what? -3 to, perfect. Okay, so I could trace from -3 to -1 without lifting my pencil. Okay, now can somebody give me an interval where this function is discontinuous? Okay, where would this function be discontinuous? As long as you cross a certain number, you got to lift your pencil to cross this number. Yep. -3 to 1. Sure. I'm being pretty liberal about my using parentheses or brackets. It doesn't matter. Okay. Anybody give me one more interval where it's discontinuous? Cody?
-1 to 1.
Yeah, -1 to 1. As long as you cross 0, you've got to lift your pencil to cross 0. Okay? How about, let's go back to the step function. What's the length of the longest interval in this graph, which I'll put over here? Length of the longest interval in this graph that would be continuous. And actually, I should probably, I think I graphed it zoomed in. Let me graph it, not zoomed in, int x. There we go. Okay, what's the longest continuous interval you could find in that function? How many units long? Matt?
Probably 1 unit.
Yeah, 1 unit. So if you gave me an interval longer than 1 unit, I guarantee it's discontinuous. Okay? How about if you gave me an interval shorter than 1 unit? Is it guaranteed to be continuous? No. I could give you an interval from 0.8 to 1.1. If you cross an integer, you have to jump up a step. 0.8 to 1.1 crosses the integer 1, and it jumps. Okay? So just because you're shorter than 1 unit doesn't mean that it is continuous in this function, but I guarantee if you're longer than 1 unit, you are discontinuous. Any questions on that? All right, so there's basically 3 different ways a function can be discontinuous. Okay, and where it's discontinuous, we call that a discontinuity. Okay, the first way we already saw was in this function. When you have a divide by 0, okay, or you have a value that's not in the domain. Okay, it's not defined at that value. Okay, so the first one is a problem because we can't plug a certain number in. The second one doesn't have a domain problem. The domain for the integer function is all real numbers. You can plug anything you want into the integer function. Okay? What makes that one difficult is that it jumps. It has these breaks in the graph. It doesn't have undefined values. It has breaks or steps. Okay, that's the second way you can have a discontinuity. And the third way is if your graph has a hole in it. This is the trickiest one to see because your calculator will not show you it. If you graph this, I guarantee everyone in here is going to think it looks continuous. The only way you can find a hole is using algebra. A graph will not help. Okay, but let me graph it and show you what it looks like. X squared plus 3x plus 2. X squared plus 3x plus 2 divided by x plus 2. Doesn't look like there's a hole in that at all. But based on the equation, where do you think there would be a hole? Yeah?
-2.
Yeah. If you go to your table and you try to type in -2, it says error because you would be dividing by 0. But you can't see it. Okay? Even if I make it bigger, you're not going to see a hole at -2. So what we do when we sketch it, if we want to show there's a hole, is we kind of exaggerate it and show there's a hole just like that. And I can kind of give you kind of another little insight into why there's a hole here. What do you get if you factor the numerator? You get x plus 2, x plus 1. And where else do you have an x plus 2? Yeah, in the denominator. So, if you want to visualize what this looks like, it's basically these cancel out and it's going to look like a line with a slope of 1 and a y-intercept of 1. But you canceled something out that caused you to divide by 0. Right? So because you have what's called a common factor in the numerator and the denominator, that's when you get a hole. So if I change the numerator, just a very small change, does the numerator factor to x plus 2, x plus 1 now? No. Now you will not have a common factor in the numerator and denominator, and it's going to completely change how the picture looks. Just by changing a plus 2 to a plus 1. So holes happen when you have common factors in the numerator and denominator that cancel out. And that's the 3 ways you can get discontinuities. All right, so one type of function that you never have to worry about a discontinuity is a polynomial. Polynomial, whether it's linear, quadratic, cubic, any of them, they are always continuous. It's impossible to find a polynomial that's discontinuous. Because polynomials, you never divide by 0. You never take square roots of negative numbers. You don't have any breaks, nothing. Okay? So polynomial functions are always continuous from -infinity to infinity. And if you have a function that's always continuous, no matter what you pick for an interval, that's called a continuous function. Okay, one of the first ones we did, I'm going to go right back to that. This is not a continuous function. it has intervals in it that could be continuous, but it's not continuous from negative infinity to infinity. Okay? So only if it's continuous from negative infinity to infinity is it a continuous function. All right, so that's the first part, continuity and continuous functions. Now we're going to tie that in with the second part, which is called intermediate value property or theorem. I think your book calls it property. It's on page 154. All right, and this kind of a straightforward concept, but I'm going to have to simplify it and kind of explain it a little bit. All right, so let me give you an example first. Let's say I have water at room temperature, like 70 degrees, okay, and I'm going to boil it. So boiling is 212. When I boil water from 70 to 212, what temperatures is the water going to go through as it goes from 70 to 212? Which temperatures? All of them, right? It's a continuous process. So if I said to you, is there a time when the water is going to be exactly 94.2 degrees? Yes, there is some time it's going to hit that. How about 187.63 degrees? Yeah. Okay, if it's going from 70 to boiling, it's going to hit every temperature at some point in the middle. Okay, and that's kind of the idea of intermediate value property. Basically says if you have a continuous function over a certain interval, okay, think of it like 70 to 212 degrees, okay, you've got something like that, then what you can find is any value between those two numbers, it will hit at some point. Okay, so if, let's say you plug in A and you plot the graph and the point is right there. Plug in B into your function and let's say you graph it and it's right there. Now if my function is continuous, it means I need to connect these two dots with some type of curve and I never lift my pencil. Maybe I go lower, maybe I even go higher, but I guarantee you I will hit every y value from here up to here. I will hit every single y value in this range. I have to, okay, because it's a continuous function from this point all the way to that point. Okay, maybe I'll hit more. Maybe I will go lower or higher. I don't know about that. But I definitely will go from this all the way to that. Okay, so if you think about that as like the water example, maybe I had water at room temperature at 70 degrees, and then I put it in the fridge for 20 minutes. So now it cooled off to like 40 degrees, and then I heated it up to boiling. So in that case, it did get a little colder before it got warmer, but I definitely went from 70 all the way to boiling. Even though I might have done a little bit more too. Okay, another way to look at it, if that way doesn't make sense, okay, you can pick any number between f of a and f of b. Okay, in my example, think of this as like your room temperature water. This is your boiling water. You can pick any number between 70 and 212. And there will be some value that you could plug into your function and get the number you picked. Okay? So that would be like me saying there would be some point in time where it hits a temperature between 70 and 212. Okay, so you can pick any number between f of a and f of b. And I'll guarantee you there's a value c you can plug into your function that will cause you to hit your number you picked at some point. Okay, that's called the intermediate value property. It doesn't apply if you have a discontinuous function. Does everybody have the top part? Okay, so it's just two different ways of explaining the same thing. If you don't want to copy both, you don't need to. Just whichever one hopefully makes more sense. All right, so I have a function, 3x minus 4. What kind of function is that? Linear. If it's linear, does that mean it's continuous? Yes. So we're dealing with a continuous function, so this theorem does apply. And I specifically want to focus on the interval from -10 to +10. I want to find a value that I could plug into that function that causes me to hit 15. Well, the first thing I have to do is figure out, is 15 even in the range of possibilities here? Okay. So how can I figure out what my lowest y value is on 3x minus 4 over this interval? Yeah, Matt?
X equals 0.
Well, I'm definitely going to hit that value somewhere. But I want to know, am I going to hit anything even lower than that? Right, x can be as low as -10. So how would you figure out how low y goes? Yeah. Let's plug in -10 for x. And I know I'm starting at -34. And it's a line, so I'm going to go up to, what's the highest value that I'm going to hit? 26. So this is a line that starts at a y value of -34, goes up to a y value of 26. Am I going to hit a y value of 15?
Yeah.
At some point, yes. I want to find that point. When do I hit a value of 15? Okay, so how would I figure that out? Yeah. Set that equal to 15 and solve. Okay, so I'm going to get 19 equals 3x. X equals 19 thirds. And if you divide 19 by 3, you get 6 1/3, which is definitely on the interval I have to be. Okay, the answer to this problem had to be between -10 and 10. So if you switch that interval and you said to me, determine a value for c between 20 and 30, such that I hit a y value of 15, that wouldn't work. Okay, because when x is 20, I'm way up at 56. And when x is 30, I'm way up at 86. So between an interval from 20 to 30, I only hit y values from 56 to 86. I would never hit 15. But on this interval, I do hit 15. And that's what they wanted to know. Okay. Any questions on that? All right, let's try this one. This time I've got a quadratic. And they're asking me to find a value you could plug in for x and see if you hit -3. Okay? Before I can even answer that question, I have to see if this is even possible. So how do I check to see if this is even doable? Matt?
Use the lowest value.
Yeah, we'll plug in the lowest value. And that's going to give me -2 squared is how much? 3 times -2. 4 take away 6. And -2 minus 4? -6. We'll come back to that in a second and ask ourselves, is that necessarily the lowest y value? Okay, remember, this is not a line. This is a parabola. So come back to that in a second. Let's plug in f of 3. So 3 squared gives me, and 3 times 3? Minus 4. 18 minus 4? 14. Is a parabola continuous? Yes. So I guarantee I'm going to go through every single value from -6 to 14 at a minimum. But it's possible I could go through even more than that. Okay? Because let's say we graph when x is -2, y is -6. Just a quick estimate. And when x is 3, y is up at 14. Okay, so way up here. This isn't a line. This is a parabola, so maybe it does something like this. So maybe this isn't even the lowest value I ever hit, but I guarantee I am going to go through all the y values between those two dotted lines. Maybe more, I don't know. Okay? And because it's a parabola shape, that means I could hit certain values twice. Okay? When do I hit -3? Well, the way I drew it, it looks like I hit it here and here. But we have to keep in mind our interval. Okay, so maybe one of these answers is not in the interval we're looking for. All right, so let me just make this a little smaller. All right, so how would I figure out where this function hits -3? Where would I fill in my -3?
Would you plug it in?
Yeah, for what?
Go far? For -3?
Where would you plug in -3?
On the y.
Yes, you're plugging that in for y, and you're solving for an x. So we've got -3 equals x squared plus 3x minus 4. Get it equal to 0. It turns out it does not factor very nicely. You need the quadratic formula. And when you do that, let's see, we get two answers, which are -3.3 and 0.3. Do I have to be careful about either one of those answers? Yeah, what's wrong with -3.3? It's outside the interval they said to examine, so I cannot use this answer. That's the only answer that's between -2 and 3. Now, let's say we got an answer of -3.3 and 5.7. Well, in that case, then it wouldn't work. But you would have already known it wasn't going to work from the original calculations we did. Okay, you would know that up front. Okay, so example 5, kind of a similar idea. I want to prove that there is a 0 in this interval. So I want to prove that this graph will cross the x-axis in this interval. I don't want to know where it crosses the x-axis. I just want to prove that it will. Any thoughts on what I should do first to try and prove that? Sophie?
Well, you can look at your range.
Okay.
And maximum to see if 0 is even.
So tell me how I would look at my range and do that.
You would plug in 0.25 for x, and you should in 0.75 for x.
Yep, and I'm going to use my calculator just to help me out with this. So I've got x to the 5th. What is it? Plus 2x minus 1. Second table. So when I plug in 0.25, I get pretty close to -0.5. And when I plug in 0.75, I get 0.74. Okay, so that's the first thing she said to do. So now what? How does that help me to prove that this has to cross the x-axis? David?
Well, I mean, one's negative,
Right,
the other one's positive.
Yeah.
So you have to go through 0.
Yeah, right, so since f of 0.25 is negative, and f of 0.75 is positive, and the other thing that's important is I have a continuous function. That means nothing if if you don't have a continuous function, because you could just lift your pencil up and skip 0. But we get f of 0.25 is negative, and f of 0.275 is positive on a continuous function. We have to pass through 0 somewhere because you're going from negative to positive. Okay, you have to. There's no way to skip it. We must pass through 0. Right, so this is basically using a combination of continuity and the intermediate value theorem to prove you have to cross the x-axis somewhere between these 2 points. I'm not saying this is the only place. Maybe you cross the x-axis 6 times in those 2 points. I don't know. But I know you're going to cross it at least once. You have to. Okay? We're not going to find where it crosses. That's all we're doing. Okay, questions on that? All right. So then last thing we're going to look at is end behavior. So end behavior basically allows us to predict what the function looks like way, way on the left or the right side. All right, so for example, when we talk about a parabola either looks like this. It's either going to go up on the right side and up on the left, or it could look something like this. Down on the left side, down on the right side. What else could happen besides these two cases? You could have up and down and down. Yeah? Anyone else tell me what's another case that could happen besides those two? Yeah?
One end up, one end down.
Yeah, one end up, one end down. And the other way as well. One side, the left end is going down and the right is up, or the right side heads down and the left side heads up. Okay, so let's examine one of these 4 cases, and I'll show you how you can describe it with 2 different notations. Okay, here's your graph of y equals x cubed. If you graph it, it'll look something just like that. So the way you describe the behavior is inside parentheses, the left side, which is represented by this, the left side is heading down. Okay, the y values on the left are heading down. The y values on the right are heading up. Okay, that's one notation you can use. Okay, the other notation you have is what's called limit notation. And first I'll describe what it is simply, and then I'll pronounce it properly. What this is saying is, what is y getting closer and closer to as x is getting closer to infinity? Okay, so let's answer that question for this one. What is y getting closer and closer to as x gets bigger and bigger and bigger? So if you head further and further and further to the right, y is just heading further and further towards infinity. Now what about what's happening to y as x heads further and further towards negative infinity? So as I head more and more to the left, it's heading down towards negative infinity. Yep. So the way you pronounce this is you say the limit of f of x as x approaches infinity, and the limit of f of x as x approaches negative infinity.
Is it always negative? Is like the limit f of x when it's negative infinity? Is x always negative infinity? Like, do they always work together?
No.
Okay.
Nope. If we look at, for example, a parabola, as x heads towards infinity, the right side heads up. As x heads towards negative infinity, the left side is still up. So in that case, they're both positive. What will always happen is your limits are always either equal to infinity or negative infinity. for polynomials, always. Okay, so there's 4 different types of behaviors. We already mentioned them. Both up, both down, one of each. So let's look at this one and see if we can describe the end behavior both with limit notation and just using the arrows in parentheses. Okay, I'm going to graph y equals x to the 4th. Okay, that's my graph on the left. What does that kind of look like? Yeah, kind of looks like a parabola. It's a parabola that's actually kind of flattened out at the bottom a little. So how would you describe the behavior on the left side? Yeah, goes up. Kyle, the behavior on the right?
Keeps going.
Keeps going up. Now let's do it in limit notation. So the limit of y, what's happening to y as x heads towards the right? As x heads towards infinity, y is heading towards infinity. And then if you look at what happens as x heads to the right, you also have to look at what happens as x heads to the left. Okay? As x heads towards negative infinity, what's the y value approaching this time? It's also infinity. Okay? If you graph negative x to the 4th, it's basically just going to look like this. It just flips it. So what would be the notation for this one? Yep. Down and down. Okay, so this time, both limits would approach negative infinity, negative infinity. Okay, just make sure you're comfortable with either the limit notation or the arrow notation. You might see both. Okay, any questions on that? So does anybody have a thought what controls, whether they go up, up, down, down? There's 2 things you have to look at. Like you could give me any polynomial. Without even thinking, I could pretty much tell you up, down, whatever it's going to be.
I'd say exponents and sign.
Okay, yep, the exponents and the sign in front. Those are the 2 things you have to look at. So basically, it all boils down to, do you have an even exponent as your highest or an odd? And is the number in front a positive or a negative? Okay, I'll give you an example of each one. Okay, this one would be something like 3x squared. Positive coefficient, even exponent. Positive coefficient, odd exponent. A down, down. Negative coefficient, even exponent. An up, down. That's a negative coefficient, odd exponent. Okay, so just by looking at the coefficient and the exponent of the highest degree term, you can tell what the end behavior is going to be. So basically what happens is it's the leading term. All you have to focus on is the leading term. If you had something like this. Okay, it's great that you get all this other stuff here after the cube term, but none of it really matters. If all you want to figure out is the end behavior, none of this makes a difference. This might cause little twists and turns in the middle. But this is the term that dominates the polynomial. It controls everything that's going to happen as far as end behavior. So if all we want is what we call an end behavior model for a polynomial, which I'll abbreviate EBM, if I want the end behavior model for some huge polynomial, all it is the first term. So the end behavior model for this function is 4x cubed. That's what's going to control the end behavior. Not the squared term, not the linear term, not the constant term. So that's what I'm saying right here. The end behavior model is just the highest degree term, which is usually the first term if you put it in descending order. So what I'm going to do is I'm going to graph this. 2x cubed minus 7x squared minus 8x plus 16. And I'm going to graph this. And I'm going to show you they basically look the same if you zoom out. Okay, if you zoom out and you look at the big picture, not the details. Okay, look at the big picture. F of x and g of x are going to look identical. So let me graph both of them. And you can really just watch this. 2x cubed minus 7x squared minus 8x plus 16 and 2x cubed. Now the first thing they tell me is do it in a window from -8 to 8 and -100 to 100. Okay, that's kind of zoomed in on the x-axis, so we're not really looking at big picture here. Okay, that's f of x. That's g of x. Do they look the same? Right on top of each other?
No.
Not really. I mean, the end behavior you can see is the same. But if we start to zoom out, okay, let's look at -40 to 40. Now we're looking at big picture. Okay, -10,000 to 10,000. Okay, so that first one is f of x. And the second one is g of x. Do those look pretty similar?
Yeah.
Yeah. Okay, so that first term, if you zoom out enough, basically is exactly what it's going to look like. Everything else causes little twists and turns in the middle that if you zoom out, you don't even see. So if I wanted to graph number 8, what term here is going to control everything that happens? And that's my end behavior model. If I were to graph just this and zoom out enough, it would look the same as all this other stuff.
-5x to the 4th.
Yep. And the behavior on this one would be what? Negative and positive, even. Yeah, this would be an upside down parabola, down, down. It could turn up to 3 times, but that's not really what you're focusing on with end behavior.
I never got started on like the last part of the end behavior.
The last part of this? Yep. You can't write the other part? That's right. But you still need the other part?
Ready?
Just kidding, you can go back to it after. Example 8.
I'm not. It's like calculator.
Okay, so end behavior model, that's a pretty useful concept for predicting the end behavior, and we're going to talk about that throughout the rest of chapter 3. We'll be finding end behavior models, which are extremely easy to find. Okay. All right, so the last problem, I'm going to skip over it. We've probably done one similar to it. It's talking about a rectangle again, but I don't want to do this one right now. Okay, so the homework tonight is on 161. Okay, and it's 1 to 6, 9 to 12, 15, 16, 21 to 25, 29 to 31, and 33. Okay, I will be after school today if anybody needs extra help. Test tomorrow. Okay, we'll review the homework before the test and then answer any questions.